Okay, let's continue regarding for the AVL tree. So last lectures we mainly talk about what? Rotation, right? Okay, so have the left rotation, right rotation, left right, right left rotation. So the purpose of rotation is want to what? Keep the tree balanced. Okay, so again, so on the tree, after the operation, you need to keep the original property. So that's the principle. Okay. Okay, for insertion step, in order to insert an element into the AVL tree, first we need to insert this key or new node, like the normal binary search tree, because AVL tree is also the binary search tree, so we can leverage their like the insert algorithm. Okay. Second, this some the characters for the AVL tree. So we want to keep the after insert is still the AVL tree. So we have to apply the step 2 to step 4. Okay. So first to update the height of a current node, check the balance factor. If it's not balanced, we need to perform the proper rotation. Okay. So that's how the insert works in the AVL tree. Converting to code, we have 4 steps. First will be binary search tree insert. Okay, so we pass the root node and the key going to insert. Second step to update the height. Third step, we need to get the balance factors. Okay, and then we need to process rotation if we need. Okay, let's look at the code, detailed code. So first is recall the binary search tree insert. Okay, so we know that. This is update height. How to get the height? How to get the update? Okay, make a recursive, right? Find the max of the height. We can newly make the update. Get balance, pretty straightforward, right? So from the height on the left side minus on the right side, right? Okay, so this is regarding for rotation. Yesterday we sort of gave some condition, okay? Which condition apply to which kind of rotation, right? So on the program side, this is each of condition to process the corresponding rotation. First, if the balance greater than 1, okay, and the key less than node left key, okay, this means what? This means on the right heavy, okay? So in this condition, right heavy. So it's process the right rotation. Oh, the process, so this is left heavy, it process the right rotation. All right, okay? Make sense? If the above the balance, right, -1, 0, 1, within this range is balanced. Out of this range is not balanced. Okay? So if you done proper, the balance factor usually is not above 2 on the AVL tree. Usually it's 2, and then you rotate that becomes within the -1, 0, 1. Make sense? Okay. And this is RR, balance factor -1. Okay, it's around -2, right? So out of the range of the balance, and the key greater than node right key, we press the left rotation. This is on the right heavy. Okay, and in this case, if the balance is greater than 1, however, the key greater than node on the left, node left child, the value is greater. It's what? It's on the left and right. Okay, on left right, we press the left right. First process what? Left rotation, and then process right rotation. All right. Okay. In this condition, balance it's less than -1. Okay, and then the key less than node on the right key value. Okay, so it's process the right and left rotation. Okay, so for this condition, you need to be clear. Okay, on each of condition. process which type of rotate to make the tree balanced. It means keep the AVL tree after insert. All right, okay. Okay, well, that's about insertion. And any question regarding for insert? No, all good. Okay, yeah, pretty straightforward. As long as you understand the rotation part. Okay, all others pretty straightforward. Deletion. Okay, what do you think about delete? Delete a node on the AVL tree. From insertion and deletion. If like you to design the step for delete on AVL tree, after delete a node, it still keep the what? Still keep as AVL tree.
Delete, check height, balance.
Yeah.
Check order.
Check order. Okay. Yeah. Delete, and check the balance factor, and then rotate. Or not? Okay. Yeah. Okay. That's right. So first, it's a what? It's a binary search tree deletion, right? Okay. We need process the binary search tree delete. So it's based on what? Binary search tree, they have the, let's review, okay? Recall this kind of delete. Have the zero leave node, delete the leave node, delete the node only have one child, right? And delete node have two children. Okay, this 3 scenario for deletion for binary search tree. And then to update height need to update, and then check the balance factor, and then process rotation. Okay, so. Yeah, still 4 step. Binary search tree delete, pass the root node and the key value, right? The value you want delete. Okay. And then to update the height, to get balance, and then to rebalance if you need. So pretty much most of the code is the same as the insertion except the first step. Okay. Let's recall how to delay the binary search tree. Okay, three conditions, right? Leave node, again leave node, 1 child, and 2 children. Okay, three conditions for delete. Okay, so you guys need to understand this logic. Okay, on the final we may have this question. Let's write the code. Okay. The support function update height same. Get balance same. Rotation also same. Okay, so question here though, why we need a AVL tree? We learn a lot, right? And design this kind of the strategy for insertion, all the common operation. Why we need this? Why we need AVL tree? Maybe, yeah, it must be something, right? Yeah, otherwise, why do we need this? Because the binary search tree is not enough to apply certain, maybe a lot of scenario. That's why we need the AVL tree. What is the advantage of the binary search tree, based on what we learned? Yeah. Disadvantage maybe we learned mainly because what? Not the efficiency, right? In some scenario. Okay. Yeah. Because in binary search tree, every case time complexity is what? It's a big O of what? Log n. But the worst scenario is what? Big O of n, right? In some cases, right? So binary search tree is probably still not really efficiency. If the case turn to the what? Like the change to the sort of linked list, right? Or screw tree, right? So that's why we need the AVL tree keep what? Keep them balanced. If they can keep them balanced, it's always what? Log O of n. That's why. Make sense? Okay, so this concept, they have linked together. Okay, it's not something you come up with no reason, right? Okay, so the come across the issue, and then we abstract the common issue, and then we invent the new data structure, and then to solve this kind of problem. Okay, so the mainly to fix the problem of the what? Plant binary search tree. So if they came unbalanced, right? So they can degrade the performance to the big O of n. That's why they try to avoid. Because they build a tree, the purpose is to improve the efficiency. Okay, if they cannot they cannot fix this issue, okay, so the problem is still the problem, right? So AVL tree can automatically balance itself to using rotation after insertion deletion, right? So all the operations what we design here, either search, either insert, is delayed, all these common operations to remain the big O of log n. Okay, so this means the AVL tree is guaranteed. Okay? Again, any disadvantage of AVL tree?
More complicated function calls.
Yeah, complicated function call. That's yeah, people fix the problem, but for the machine, probably not machine problem, right? Right? Yeah. Maybe on the exam, you have more time to remember and the logic. Yeah. So, but it's not a machine problem. What a disadvantage? It's already big improved, of course, right? For the binary search tree compared with binary search tree, but the compare itself, is there any disadvantage? Nothing is perfect, right? Always have some problem. Even though you think you can improve that, you still have an issue, right? You fix one thing, you come across another thing, because you have a rotation. This means every time you do the operation insertion deletion, you probably do the rotation to keep the strict balanced. That may cause the issue, even though improve a lot compared with the binary search tree, but still can be improved, right? Still can be improved, yeah. Because AVL tree is strict balance, that's why you have to rotate a lot. Every time you did the insertion deletion, you rotate. Every time to do that, okay? So the AVL tree is strict balance, but and then the researcher can think, okay, let's come up, make a compromise. We don't need a strict balance. We need a little weak balance, right? Like a balance factor equal to 2, maybe 3, 2 or 3. It's still okay, right? Won't be reduced a lot of performance, right? So we don't need to rotate it very frequently. So they come across another tree called red-black tree. It's not required for this course, but I strongly suggest you guys can learn about this, either YouTube or any Wikipedia, any ChatGPT, okay, to know about this tree. Because the reason is building in library using this, okay, not AVL tree. All right, okay. On assignment, first assignment question is regarding for tree, TRIE, not TREE, TRIE. And you guys, I hope you guys can look at that. That's more practical. Using B a lot on the application, autocomplete, all these kind of features, the dictionary, how the file being stored, is being using well. Yeah. So it's not teaching this course, but I hope you guys can really know about that. At work, you may come across more or less. Okay, good. So this is the weak balance. Binary search tree is red-black tree. So since we don't have much of the rotation for red-black tree is good for frequent insertion deletion. That's common sense, right? Okay, once we design that, okay. But for search, which is better? AVL tree is better because it's always balanced. Okay. Select is better, but okay. But people can compromise. It's a chicken egg. Which one you want? Always have balance. Okay. Always have a balance. Some example here. So on the index on database, they using the AVL tree for indexing. So when you design database, in some searching scenario, you need to index the data to improve the searching speed. Okay. So interview question: how you can speed up the searching, like a SQL query or something to search. you can apply, okay, I do the index. Okay, it's not binary tree, but you do the index. On the database solution itself, firmware, like MySQL, SQLite, and we're now and also the Microsoft, right? Microsoft SQL Server, PostgreDB, they all have the index features to able to speed up the searching. So similar within the index at the book. Okay, so that's a good example regarding for AVL tree for applied. Any question regarding for the binary search tree, AVL tree? Okay, this analogy, everything is linked together, okay? First, the general tree, we conclude the algorithm, okay? And then solve one type of problem, but a lot of problems cannot be resolved. And then they invented the binary search tree and solve the certain problem, but still not enough, invented into the AVL tree. Okay, but now more and more trees coming up to solve the certain problem. Okay, so now you can see a lot of tree. We just learned maybe some fundamental tree. Okay. All right. Okay. So next we need to learn about Heap. Have you heard about Heap? Yeah. Yeah. If you do the Java. Probably not many doing the Java. They call the garbage collection. You mentioned about garbage collection, right? They're on the heaps, right? But that different meaning, okay, for terminology. On data structure, the heap is what? It's also the tree-based structures, okay? So that satisfies the heap property. What called heap property? So two types of heap. First, max heap. So it means every parent node is greater than or equal to these children. So the parent node always greater or equal to their children. Second is minimum heap. So the value of parents is always less or equal to their children. A two type of heap. Heap is not a sorted sequence, okay? Not sorted structure. So it's only can limited parent and children. They know the parent is a greater or equal or less than equal, but they don't know all the sublinks, the relationship between this. They don't know. So that's why it's not sorted sequence. Okay, not like a binary search tree. They based on the sequence order on the in order traversal. You can get a sequence like order sequence, but not for the heap. But I call the weak sorted, because some of the data can link up, not everything, not pure random, okay. But this can solve a certain problem, okay. So it's not a pure random, but you can get a certain of the link between some portion of the data, okay. So purpose we design this is for what? Want to quick access for the what? If you give you a sequence of data, not stored. If you put as a heap, you can quick access either maximum number or minimum number, because based on the properties, the parent node always greater or less, right? So you get a maximum or minimum number. It's what? Big O of n. That's a constant, right? First, the root element. Right, root node of this tree, you can get either maximum or minimum value. On the heap, now they have a lot of type of heap, subtype of heap, but in this course we focus on the binary heap. Okay, you may come across some other heap, regex heap or Fibonacci heap, whatever, but this course we focus on the binary heap. So the binary heap, we want to keep this tree as what? Called the complete binary tree. Okay, a different type. It's not binary search tree. It's a complete binary tree. What's a complete binary tree? If you remember, what's a complete binary tree? Forget. All be filled, right? Except what? Except the last one. Okay. So all the level will be fully filled except the possible last, which is filled from left to right. Okay, so for the complete binary tree, for the heap, we design the complete binary tree. For the heap, that's the principle for what? Once you design the operation, insert, deletion, you need to keep the heap as a heap. Okay, still keep it as a binary, complete binary tree. That's the fundamental for that. Okay. After any operation, the heap turn also the heap. Okay, cannot be changed for other type of tree. Okay. For example, this one. What do you think about this one? It's max or min? It's a max heap, right? Maximum heap, because the parent node always greater than the children, right? The value. Okay. This one will be the what? Minimum heap. Okay. So as we can see here, if we go through the traversal, any traversal, the maximum for this list is what? It's a root node. Okay, 21. That's why we can access the maximum number in this list. Well, very quick. Okay. This case, the root node 1 is a minimum number for this list, right? So you can access for the minimum number very quickly. Okay, call min heap. Okay. So for the heap here, okay, for the heap, if you try to create an array, by the BST, breadth first traversal, we can get this. Okay, breadth first traversal, still remember, right? From where? 21 and 1 by 1. Okay. So this is an array here. The purpose of heap we want to convert is array. Convert is array because array have the good advantage for what? To access the elements very quickly if you know the index. Okay? So that's why if you want to design the heap, you convert it as array to work on that. Okay? Now linked list is array. This is the index. Okay, for node at index I, for example, any index, this index, right, I here, how to calculate the parents? It's 9, right? The parent should be 17. Right? It's 17. If we know index 9 is index 4, how we can get the parent? How we can know this is 17 the parent? You know? How do we know the 1 is the child? So that's a question here. We want to use the index, but we use a binary index, right? A binary heap. So we only have 2 children for each of node. We can come close the formula to find what? Their parent and their children. Make sense? On the array. This is the formula. Left child, we know index I. On left child, 2 times I plus 1. That's the left child. Right child, 2 times I plus 2. The parent, I minus 1. Divided 2 is 1 on 1. For yeah, floor division. Just only for the integer piece. Make sense? Make sense? No? Let's have an example here though. Okay, field 4. Find their parent. 4 minus 1, 3. Divided by 2 is 1. 2, 1, 17. Okay? Let's calculate the left child. I equal to 4, right? I equal to 4, you can see that, right? I equal to 4. 2 times 4 equal to 8 plus 1 equal to 9. 9 into 1, right? And then on right chart, 2 times 4 into 8 plus 2 equals 10. Out of range means we don't have a right chart. Okay? How to get this? How to sum up this solution here, like this kind of equation? How? Because we go through within the Bragg force traversal, that's why. Okay? On that force traversal, you won't get this kind of relationship. It's from the what? Root, and then something from here. Okay. Each of the nodes have what? Two differences, right? Okay, that's why. Okay. So once you apply once you want to have a support function to support your logic, okay, so you supply the what? Supply the proper methodology is make a big difference, right? So if we know this kind of relationship, we can use an array to solve the problem within what? Within the tree. Okay, so we can improve the efficiency a lot. Okay. People are smart. Yes, I just found that people are so smart when I look at this. All right, okay. A lot of scientists is really smart. All right, okay. Main operations regarding heaps. Insert, of course, we have insert. And we get what? We want to, the purpose of the heaps to invent this kind of this tree structure is because we want get the maximum or minimum, right? So we have a function to get the maximum or minimum. Also, we want what? We want to get the maximum and minimum. Okay, so we have the what? Extract minimum, maximum or minimum. Okay, so it means the maximum will be released from this tree. Okay, and then to update the value, right? In this tree, we want to make an update, and then we want to build. There's any way we give the unsorted sequence. We want to build the heaps. Okay, so if the purpose, okay, I want to know very fast to know about the maximum number in this sequence. We want to build the maximum heap from this array list, right? Or we want to know the minimum number for this array list. Okay, we're going to build what? Minimum heap. Okay, that's how they design this kind of the operation for this particular heap structure. Make sense? Is there any delay? Why don't have delay? Delay for feature. they do have delay. This is the part of delay. Okay. Make sense? But the purpose for maximum and minimum value. That's just so. This is for this. Build for this for you. Okay. Insertion. On the insertion, we need to build up something support feature. Because the purpose what principle again? We insert the element into heaps. That's still the heaps. Okay, that's still heaps. So we need like the AVL. If we insert elements into AVL tree, they need some support action. Like rotation, right? Rotation is a support action. So the same thing with here. Let's look at this example here. If we want to insert 5, okay, in the tree, want to insert 5, what we do? We just find what? Okay, how to insert into the binary tree?
The lowest rate.
Lowest, yeah. Just find this one and insert, right? Okay. So once we insert here, is that still the minimum heap tree? Minimum heap? Why?
It's 10 is greater than 5.
What?
10 is greater than 5.
10 greater than 5. So that's break the rule. So we need to find a way to what? Now rotate, yeah. To rearrange this node, okay? To keep them as a mini heap. Okay, let's bring up this formula again. Okay, you guys need to memorize formula. Not hard, but you guys need to memorize formula. 2 times I plus 1 is the left chart. 2 times I plus 2 is the right chart. I minus 1 floor divided by 2. That's the parent. Okay. Okay, let's see how we can rearrange. Okay, let's see how we can rearrange. In this case, if we want to insert 5. So we want to find what? Their parent. Okay. So if we insert, we'll be insert at the what? To the last right here. For the 5, we can calculate here how many? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, right? 13 minus 1, 12 divided by 2, 6, right? 0, 1, 2, 3, 4, 5, 6. Okay, 10 is their parent. So they want to compare 10 and 5. So 10 is greater than 5. We need what? We need the swamp, okay? So it's in the swamp, right? After swamp, become like this. So far, this is array. Don't think about linked list, okay? This is array, just a quick swamp on the array, okay? So 5 become turned here, and the 10 become here. And then what we can do now? Next.
Check it with the next parent.
Check again, okay? 6, right? So their parents, same way to calculate. 0, 1, 2, 3, 4, 5, 6. 6 minus 1, floor divided by 2 equal to what? Equal to 2, right? Okay, so it's 0, 1, 2, 6, right? You get the 6. 6 above 5, doing the swap or not? Yeah, when you swap again. Okay, after swap, we become like that. Okay, so this also swapped. Okay, so the 5 put here, 6 become here, just swapped. Make sense? Okay, so the you won't see on the computer. Okay, you just visualize. What you do is here. On computer, you're doing is array. Make sense? Okay. So it's been swapped. Again, what do we need to compare? Okay, compare what? 5, the parent, right? Okay, the parent equal to what now? 4, right? Okay. Do we need swap? We don't need, right? Because 4 is less than 5. So it's done. So now they become become the minimum heap. Make sense? Okay. Okay, so they have a terminology called to describe this this kind of algorithm called shift up. Okay, not shift, but shift up. So it means why is shift up? Because this element move up and out. So we have a shift up, also have a shift down. Okay, one another way, right? Okay, let's look at code though for shift up. Once we know the logic, let's apply the code. The code is very straightforward. Take a while loop. Okay, first we need to find the parent index. Okay, so we pass the index, right, and find the parent index, and then we operations all on the array. Okay, this time there's no linked list, no pointer. Okay, all is array. So we want to compare the insert node, insert value, and what parent value. If you need, swapped. Redefine the index value to the parent. Okay. Otherwise, if they don't need swapped, just break. Okay. Once you finish that, that's you become the what? Become a heap structure. Okay. This is a shift up. What time complexity for this process? Log n. Okay. Okay, let's look at this scenario. Okay, look at this scenario. We described we have the shift up, we also have a shift down. Okay, so this is not part of insert, but let's look. I want to describe the shift up always happen on the insert, but shift down we look after. But I want to introduce shift down here. Okay. So it's still min heap, right? Okay, let's process the breadth first traversal. We can get array. Okay, this is array. Okay, so this is how we calculate the children, the index of children and their parent, right? Do you find an issue here though? Minimum heap 7 greater than what? Than 4. Okay, 7 greater than 4 is not min heap. So we want what? We want to make a shift down, become into the min heap. Okay, now what we can do here? We make comparison. Yeah, on strip up we compare with the parent, and the strip down we need to compare with their children. Okay, both children. Okay.
Do you compare like left to right or right to left? Does it matter?
Compare. So far the code is left to right. Okay, so on the tree, most of the case we use left and right, except there's any customized or any specific required. Okay, so 8 greater than 7, that's okay, right? So this note is okay. Now I shouldn't say a note. The left chart is okay. The value on the right chart is not good, right? Because it's 7 greater than 4, right? So from 7, we can calculate what? The index of the right chart, okay? Is 0, and then it's 2, right? 0, 1, 2, right? So right child 2, okay? We need to swap, right? 7 and 4 need swapped. Now being swapped. Okay, so it means what? 4 goes up, 7 going to the right place. Okay, and then what do we do here? Pair what? Compare. Okay. So 6 is okay. 6 is okay? No, because 6 is less than 7. 10 is okay, right? So this case is left child. It's not okay, but the right child is okay. Okay. So this case we also need to swap again, right? It's between the 7 and 6. Okay. Now this is being swapped. And then let's continue compare. Now it's okay or not? 7 less than 11, left child. 7 less than 9. So now it's good, right? So it's done. Okay, so after this, so this become a what? Min heap. So we call the what? Shift down. Okay? Shift down. So this is a code for shift down. A little bit complicated because they compare with not only parent. Before shift up, just one parent, right? But now they have 2 children, right? Compare both, and you can find out which children need to swap. Make sense? Okay, so still take the while loop. Okay, once the index less than the size of n, going to process. We calculate what the index of left child and right child. Give the what candidate is in the middle. They can find. So this part is mainly to find out which one is not okay. It means it's going to need swapped. Okay, this part, and then this process is swapped. Okay. Now shift up, shift down. What about this complexity? Again, log 12n. Okay, log 12n. Question? No question. Okay. Why is log 2 of n?
Every time you go down, you're halving the amount of nodes you're comparing.
Yeah. Always, you can always ignore a part, right?
Yeah.
Okay. Yeah. Now we build up insert. Okay, how we can do an insert? We push a value back into an array, and then we process sweep up. That's all about for insert. Make sense? Yeah. Okay. What's the complexity about insert? Same.
Log n again?
Yeah, same, right? Because it depends on here.
Constant.
Yeah. Okay. Yeah, it's a constant. This is a log n. That's why. Okay. Yeah. All right. Any question regarding for insertion for heap? Maximum heap is apply the same logic. Just compare within the which is larger, right? Same principle regarding for minimum heap. Okay. Okay, got minimum max. For example, we want to get the minimum of the value. This is the minimum heap, right? So if the minimum heap, we can get the minimum value easily, right? Just the what?
0.
Just here. This means what? Index of 0. Okay, index of 0, 4. So pretty straightforward. That's the code. Mainly this part, return the data 0, first elements of the array. Okay, so let's just check some other condition to check whether it's a minimum heap or not. If not, you won't get a minimum number, right? Okay, so if this the array is empty or not. If it's empty, this means what? The heap is empty. Okay. All other cases, it's if this is the minimum heap, just return the first elements of the array. Okay. Time complexity, big O 1, right? Very fast. Maximum heap, to get the maximum number of this array of list of the number, right? So same code. Okay. First check whether it's maximum heap, and then check whether it's, this array is empty or not, and then to return what? First element of this array, so we can get the maximum value for this list. Again, complexity is big O 1. Okay. All right. So extraction. Want to extract the minimum or maximum number? How to extract? For example, this is minimum heap. We want to grab the 2. We want to grab this 2. We just grab it.
Taking it out, or are we just looking at the max value?
What?
Are we taking it out, or are we just?
We're taking it out. Extract means we take it out. Just look at the minimum value. We're just using the get minimum or max, but we want to take them out.
So it will no longer be in the tree.
No longer be in this here.
So would you then shift and rotate?
Yeah, we need to use the shift down. Okay. Yeah. Well, earlier we introduced shift down. Insert we use shift up, but in this case we use shift down. How that works? How that works? Okay, so this kind of delay. If you want to delay this node 2, how we can do? Deletion, logical deletion. You guys still remember? Not just delayed. How to delay it on a binary tree?
Set it to like invalid, soft deletion.
No, we have to grab the what? Minimum impact of this tree. What's the minimum node impact for this tree? This value. So remember?
Oh, so swap it.
And then to replace, right? And then delay which one? This one.
Yeah.
Make sense? Okay. Then we do what? Swapped. And then remove 2. That means 2 being delayed. That's a logic for deletion in a binary tree.
And then sit down.
Yeah, because you guys need to remember this, okay? How to delay the node in binary tree? It's not actually delayed, directly delayed. You have to find the minimum impact of the node to replace that, and then to delay the value. Okay. So now, what do we need to do? This tree is not what? Minimum heap. Because the gains already, right? And then we need to swap down. Okay, now entire thing let's see how that works, right? And swap down. So the 10 now is on the first element, right? Okay, definitely this is not a minimum number, right? Okay, how that works? Compare.
5, here, 4.
Yeah, compare 5, compare 4.
7,
Okay.
6,
Yeah, in this case, which going to swap?
4.
Not 5, because 5 is less than 10, 4 is less than 10.
Right.
Which one?
4.
4, you guarantee? Any question? 4, right? Okay, so the minimum number is 4. On the code, earlier you saw the code is 4. Okay, check the left and then check the right. Find the minimum number, okay, to swap. Okay, 4, right? We do a swapped. Now swapped. Okay? What next?
7, 6, we'll swap to 6.
Swap with 6, right? Okay, same logic. 7 and swap. And then it's good? Good now? It's good. Okay. Now it's done. Okay. Okay. What?
Even though the 9 is still, it's fine, even though the 9 is still lower, should it not swap the 9?
What swap? Swap and 9?
Locality.
This one?
Okay. Yeah, so it doesn't matter.
Swap and what swap?
They're like local to their respective subtree, right? So just because 9 is lower than 10 doesn't mean it needs to swap.
No. We just look at the. So they don't need to sort it. They just care about their
Just
parent and their
order?
child.
Okay.
Okay, they're not sorted. Okay, they just care about
Locality.
their parent
Is
less than their children. That's it. Okay, that's it. That's a heap. Okay, yeah, you may can invent some new tree, right? So something to some swap, solve one type of problem. Maybe you can grab a new tree, right? So, yeah, so you can invent a lot from this kind of concept, right? So it's just okay. Some certain problem comes, so this can solve the certain problem. So this problem want to what? Access the minimum maximum number in this list very quickly. So that's for heap the purpose. Okay. All right. This is the code. All right. Okay. This is just to check whether it's empty or not. And then what we do? We have minimum value equal to the first element, and then we find the what? Swap the value from first and last swapped. Okay. And then pump back. Last one pump back. And then we're doing the shift down. Okay? Makes sense, right? The coding makes sense. Okay? Time comes again.
log in.
Huh?
Log in.
Log in, yeah. Because it depends on this one, right? Okay. Okay, so for maximum heap, it means we can extract the maximum of element. Same principle. Okay?